Good morning, everyone. Let's get our start here today on chapter 12. So we're actually only going to cover part of section 1 out of chapter 12, so we're not going to talk too much about this particular chapter. There'll likely be 1 or 2 questions from chapter 12 on the final, so I don't want to spend too much time on the chapter. But we're going to talk about how we can classify solids based on the type of bonding that takes place within the structure of the solid. So we're going to try to classify a few different types of solids based on their formulas and talk about some of their physical properties, and then we'll describe some of the differences between a crystalline versus an amorphous solid. And then we're not going to talk too much more about some of the finer details of structure. We're not going to talk about metallic bonding in much detail, other than showing a couple pictures of it so you can try to understand on a cursory level what goes on within metallic bonding. And then we'll show you a couple pictures of ionic solids, but we're not going to expect that you memorize or really solve many problems based on a few of the pictures that we'll see. And when we get to some of the things, I think hopefully it's clear what we want you guys to know out of chapter 12. So what we're going to do is go through a few different categories. We're going to go through molecular versus ionic versus metallic. We'll also look at things like polymers and covalent network solids and try to describe some of their differences. So our first category of types of solids would be a molecular solid. And so a molecular solid are where we have molecules that are held together by their intermolecular forces. And so this is if you imagine taking things that tend to exist as gases or liquids at room temperature, things like water, things like oxygen, nitrogen, CO2, and you lower their temperatures until they reach the solid phase. When things like water, CO2, etc. are solids, those molecules are held together by the same type of forces holding the liquids together. So these are being held together by things like hydrogen bonding forces if the molecule contains hydrogen bonds. So the molecules are held together by our IMFs like H bonding, dipole-dipole forces, and then dispersion. And of course, the types of forces a given molecule has depends on the nature of the molecule. So nonpolar molecules only have the dispersion force. Polar molecules, but those that don't have H directly bonded to NO and F, would have dipole-dipole and dispersion forces. And then things like water, things like HF, things like NH3, where you have hydrogen directly attached to NO or F, then would have all 3 of those forces, H bonding, dipole-dipole, and dispersion forces. And so the same ideas would apply as we were talking about in the liquids chapter. So the molecules that have hydrogen bonding forces would generally have a stronger set of intermolecular forces if we're comparing them to comparably sized molecules that only have dipole-dipole forces, or to comparably sized molecules that are nonpolar and only have dispersion forces. And so we can compare, or we can look at some of their structures as generally the solids aren't very strong. You're going to get a softer type solid. They're generally going to be electrically insulating. You're not going to think of an ice cube as being a conductor of electricity. So when we say something is an electrical insulator, we usually just mean that it doesn't conduct electricity. You're not going to use molecular solids generally to encase a wire. You're going to want to use something more like a polymer. We'll talk about that a little bit later. But these melting points are going to be so low that these substances are often going to be liquids or gases at room temperature. So we have low melting points, lower boiling points for these substances. And so there's a tremendous number of examples we can give, like water, like we already mentioned, O2, CO2, et cetera. But some other examples could be like hydrogen bromide, HBr, melting point and boiling point, still well below room temperature despite being polar. So this molecule here would have dipole-dipole forces and dispersion forces, but still is a gas at room temperature because its boiling point's well below room temp. Acetonitrile, melting point below room temperature, boiling point above room temperature, so this is a liquid at room temperature. Iodine has that melting point well above room temperature, boiling point, of course, even higher, and so this is our solid at room temperature. We might recall F2 and Cl2 were gases at room temperature, Br2, bromine's a liquid, and I2 is a solid. So despite I2 being nonpolar, and only having, therefore, dispersion forces, the fact that it's really big, it has really high molar mass, allows it to have a particularly strong dispersion force, allowing it to have a strong intermolecular force of attraction. So when we're comparing H bonding to dipole-dipole to dispersion forces, we have to compare comparably sized molecules. If a molecule is just bigger, it could have a strong dispersion force like I2 does. Sucrose is a sugar, has a lot of hydroxyl, the OH groups on it, so it has a lot of hydrogen bonding capabilities. So it's a polar molecule, H bonds, has a really high melting point. As a result, it tends to decompose, doesn't really tend to vaporize like some substances do. So it's just going to decompose and caramelize, but it's obviously a solid at room temperature. And so it has, the relatively strong set of H bonding forces from the hydroxyl groups. So a lot of hydroxyl groups on sucrose, so the H bonding force is present there. Okay, so molecular solids, low melting points, boiling points, because we have a relatively weaker set of attractive forces between molecules. So if you're thinking of the strength of attraction of a dispersion force versus a dipole-dipole force versus an H bonding force, those are not as strong as covalent bonds. So when we looked at covalent bonds in chapter 8, a covalent bond is in like the 200 to 400 range for single bonds, even higher for double and triple bonds. And so covalent bonds are, in the hundreds of kJs per mole. Our dispersion forces, dipole-dipole H bonding forces, are in the like 5 to 50 range of kJs per mole. So not that strong of a force of attraction, not as strong as a covalent bond, not as strong as an ionic bond. So if we look at our ionic solids, these are the cases where we have extended networks of atoms that are held together through the electrostatic forces of attraction we call the covalent bond. And so we just have our alternating plus minus charges. And so we have our electrostatic forces of attraction. We have the idea of Coulomb's law. So the energy of electrostatic attraction, we have plus and minus particles, is described by Q1, Q2 divided by D. And so we know we have this attractive set of forces. We know that ionic bonds are generally going to be stronger when we have more highly charged ions. So if you can make the ions higher charged, if you make the ions closer together, we know from lattice energy in chapter 8 that that's going to make for a stronger ionic bond. And so we want higher magnitudes of charge. And we want the distance of separation, the size of the ions, to be smaller to give us the highest energy magnitude of attraction. And so 2 plus 2 minus better than plus 1 minus 1. Smaller ions better than bigger ions here when we're exchanging charge. And so we think of table salt, you tend to think of a structure that's more brittle. You might imagine having a big crystal that you can kind of like hit with a hammer and then break apart into smaller crystals. And so we have a brittle structure because you can just sort of break the structure and it just can continue to exist because it's just alternating plus minuses. And so you might have a big crystal that has millions and millions and millions of ions. You could have a smaller crystal that only maybe has thousands of ions. But still, we just have alternating plus minuses. Now, the electrical properties might be a little confusing at first, that an ionic solid itself, just as the solid, tends not to conduct electricity very well. What this means is it's not really easy for us to put an electron in or out of one of these ions. Like the ions are stable with the plus and minus charges. They really don't want to lose another electron. The plus ion really doesn't want to gain another electron. And so to be an electrical conductor, you have to be able to pass electrons to and from each other. The solid structure of ionic solids actually don't do that very well. Now, we know if you can dissolve in water, it's a different story. We know in water, it's conductive if soluble. So if you can dissolve the ionic solid in water, then water, which itself isn't very conductive, then water becomes more conductive, becomes electrolytic, with the ions being present then in solution. So individual ions can conduct electricity because they're going to pass the electrical charge to and from each other, but they're not going to do that very well in the solid form. So it's kind of interesting that as solids, ions are not good conductors of electricity, but in water they are. And so ionic solids, if you go back to then thinking of sodium chloride solid, magnesium oxide solid, those solids are going to have a high boiling point, high melting point because of the strong nature of that electrostatic force of attraction. So our ionic bonds are generally on the order of magnitude or stronger than covalent bonds. And then you have an extended network. So instead of having like water, where you have hydrogen, 2 of them attached to an O, and then the other O's have that weak intermolecular force of attraction, NaCl or MgO, these compounds benefit from having plus, minus, plus, minus, plus, minus. So you have every ion connected to other ions throughout the structure, so you get a collection of covalent bonds that are really strong in their nature. And so if you look at some of the melting points here, lithium fluoride's melting point, 845 degrees C. So really high melting point compared to our molecular solids. Look at the boiling point over 1600 degrees C. Now sodium chloride compared to lithium fluoride is just bigger in the case of sodium, bigger in the case of chloride compared to lithium fluoride. It has a weaker lattice energy. The weaker lattice energy then leads to a lower boiling point. So boiling point is generally going to be directly proportional to lattice energy. So if you can imagine lattice energy decreasing with size increasing, then the boiling point also generally decreases with that same trend. So boiling point is tracking with our force of attraction. Just like in the case of molecular compounds previously, stronger intermolecular forces, higher melting points, stronger ionic bonds, higher boiling points, weaker lattice energies, weaker ionic bonds, lower boiling points. Strontium oxide, 2 plus, 2 minus, going to have a much higher melting point as a result of its much higher lattice energy. So look at its boiling point over 3200 degrees C. It's kind of interesting you can boil this compound. I've actually wondered if that's really something you can do. But must be a tricky experiment to get up to that temperature, let alone boil off this substance. But melting point above 2500 degrees C. Calcium fluoride, 2 plus with a minus, kind of in between. So here we have a 2 plus, but with a minus ion. So we're not quite as high as the 2 plus, 2 minus, but not quite as low as the plus 1, minus 1. So again, tracking with lattice energy. So our ionic solids described really just by their lattice energies out of chapter 8, kind of a reinforcement. If you can predict lattice energies, you can predict melting point trends for ionic solids. Now, a category of solids that are really important, but one that we really, I don't think, have paid any attention to in the class, are what we call covalent network solids. And there's a tremendous number of important compounds that exist with this structure, things like diamond, things like graphite, things like glass, quartz. A lot of the items in the chips of a computer chip are held together by covalent network solids. And so these are extended networks of atoms held together by covalent bonds in like 3 dimensions within the structure. And so this structure here is actually diamond. And what diamond is, and I think I have mentioned this, but we haven't really seen a picture of it, is it's just a series of tetrahedral carbon atoms connected in 3 dimensions within a structure. So it's literally just taking the idea of a tetrahedron and then just replicating that structure in all 3 dimensions. So then we just keep taking each carbon. It's hard to draw, so it's maybe better to look at the picture. But if you get the idea, it's like you're just taking a tetrahedral structure and just replicating the tetrahedral structure in all 3 dimensions all throughout the structure. And so what you end up with is a structure where you just linked all the atoms by that very strong covalent bond. So we have all of our atoms linked together with a strong covalent bond. It's kind of like the ionic solid version of covalent bonding. It's where if ionic bonds gain strength by having alternating plus minuses in all dimensions, here we have covalent bonds in all dimensions. And so we get a very hard structure here, meaning that the structures can be tough, sometimes brittle though. So you can still sometimes shatter a covalent network solid, even though they're also in some regards hard. So you can often use diamonds and saw blades because they're strong enough to cut through items. But if you hit them with a hammer, sometimes they'll shatter too. So it's kind of interesting that a property can be hard but also brittle. The electrical properties are kind of interesting. They're often semiconducting in their properties, meaning that they have some ability to conduct electricity, and often it can be turned on and off with like switches. And so you can find ways to vary the conducting property depending on conditions. That's what makes some of these materials good for computing, and the fact that you can turn them on and off. And so the conducting properties are kind of in the middle of conductors versus insulators. And so it allows them to conduct electricity usually on demand, which makes them good for computing purposes. And so melting points, boiling points, also generally really high. Let's look at a few examples. So if we imagine the atom here is silicon, so if silicon's replicating in 3 dimensions, silicon's in the same group as carbon, so it forms the same type of diamond type lattice. 1400 degrees C melting point for silicon. Diamond's melting point, I'm not sure why I don't have it on the slide, but diamond is about 2,500 degrees C melting point. So really high melting point for the three-dimensional structure of covalent bonds for the carbon atom. So boiling point is also very high for these compounds. Germanium, in its structure, 900 degrees C. Gallium phosphide, 1,400 degrees C. Silicon dioxide and glass, 1,600 degrees C. So we get glass, SiO2 from quartz often. I'll show a slide a little bit later on taking quartz where you might mine it and how it has a crystal structure to it, and then we end up melting it down, reforming it to make glass, where glass is an amorphous structure, but we'll talk about that in a few slides. So really high melting points for the case of compounds where we have three-dimensional arrays of covalent bonds. So these are kind of, again, like the ionic bonds replicating in 3 dimensions with electrostatic forces of attraction. These now are atoms replicating in 3 dimensions through the sharing of electrons overlapping in the covalent network solids. Okay, so polymers, I mean, you can take a whole class of polymers. So there's really not a lot of justice you can do to a whole class of compounds that we haven't talked really at all about on a single slide, but we'll try to describe polymers here real briefly. And so if you can imagine taking a chain of atoms, we're going to link them together through covalent bonds within maybe like a strand of atoms. What this would be is, imagine you take something like CH2CH2, and then you just replicate this like up to 1 million or more times, where you just have some sort of group that's going to replicate. That's the basic idea of a polymer. And so then for polymers, you can have like polyethylene, where you're replicating the ethyl group kind of ad nauseum in the structure. And so polyethylene, which is, I think, basically like our saran wrap type plastic, alternating CH2CH2 groups. If you replace one of the CH2s with a chlorine, then that's polyvinyl chloride. That's like the hard plastic you think of as being like the dashboard of your car. And so harder plastic is where we're now taking CH2 and then a CH2 or a CHCl group. And we're replicating this group here. So then you can start, maybe replacing one of the hydrogens with like a phenyl group, the C6H5 group. That's polystyrene, that's styrofoam. So we get a styrofoam structure, and we're replicating where we replace one of these hydrogens with the C6H5 group. And so that's like the benzene type ring. And then a rubber structure is like a C5H8 group being replicated ad nauseum through the structure. So polymers are long chains of atoms held together through covalent bonds. And then the different strands of a polymer, if you imagine polyethylene where we have a long chain of hydrocarbons, there's going to be another long chain of hydrocarbons and another long chain of hydrocarbons that then have their attractive forces through dispersion forces. So the strands of polymers are then cross-linked, not cross-linked in the sense that they're covalently bonded together, but they're linked together in a sense through dispersion forces. And so it's those dispersion forces through strands of polymers that give them their overall properties. In fact, the word cross-linking comes up with like car tires. So car tires are actually chemically cross-linked through a process called like vulcanization, where you actually use sulfur atoms to interconnect strands of the polymer. So if you imagine having something like the C5H8 group replicating on a strand, you have another strand, and then you find a way to chemically, through covalent bonds, interconnect the strands to get an even stronger form of rubber. And so a rubber band might be this structure here. You vulcanize, cross-link the strands of the polymer for something like a tire to give it more strength. And so the properties of a polymer will vary tremendously. The ones here we tend to think of as being more insulating in their properties, so that these are often used to encase a wire. So the wire, if you have a conducting wire, we'll talk about metals in a minute and why they're good conductors, but you have a good metal conductor, insulate it with some type of a polymer to insulate the wire. You can make conducting polymers. So there's a whole class of polymers that are conductive polymers, but you can prepare all different kinds of repeating groups, and then depending on those repeating groups, end up with a wide variety of properties. You can have all kinds of melting points and boiling points too, but generally you're thinking of these compounds as melting and burning and not really going through a typical boiling point process. So these compounds here would tend to decompose if you start heating them too high. So the melting point's not particularly high here, but it's really just because you end up like just breaking a strand, and then that just kind of breaks the whole process of the polymer and decomposes it pretty quickly. But again, you can prepare polymers that have higher melting points and handle heat better than others. And so polymers are an incredible class of compounds. Again, you can have a whole course, or even you can do a PhD in polymer science. So I mean, we're just kind of introducing the topic of the category of polymer solids here on this slide. So long chains of covalent bonds, and then the chains cross-link through dispersion forces, or even stronger cross-linking in like car tires through vulcanization, where we chemically link those through covalent bonds. Now, one of the more important categories of solids that also is one we don't talk about a whole lot are metallic solids. We talk about metals a lot. We talk about some of their properties. We talk about metals like in chapter 4 when we're talking about oxidation and reduction, but we really don't talk too much about the actual structure of solids and what's holding metals together. But metals are held together through extended networks of atoms through what we call metallic bonding. Probably the easiest way to describe metal bonding is just called, well, it's metallic bonding is what's holding iron together. Metallic bonding is what's holding sodium atoms together in sodium solid. So if you imagine any metal solid, or in the case of mercury, mercury liquid, what's holding those atoms together is what we call metallic bonding. We get relatively strong bonding here, so we're going to get a strong structure. Most metals are malleable and ductile. That means you can pound them into sheets. You can stretch them into wires. So the pounding into sheets is malleable. Ductile is stretching into a wire. So you can make most metals into a wire. Who's watched Breaking Bad? I make all these Breaking Bad references, and as time goes on, so few people have watched it. One of my favorite scenes in the show is when they're out in the middle of the desert and the battery on the RV won't start, and so Walt makes like this makeshift voltaic cell to try to start the battery, and then he makes the two sides of the battery with the and he's like, what would be the perfect element to conduct the electricity? And Jesse, his student from high school chemistry, who didn't learn chemistry very well, goes, wire. And Walt wanted him to say copper. And so copper is the element that would be best conduct electricity. And so metals are good conductors of electricity, and you can stretch them into wires too, which makes them also particularly suitable for that task. So if you can stretch a conductive substance into a wire, then the wire can conduct electricity, and that works out pretty well. So the conductibility, like why metals are such good conductors of electricity, we'll see this in a structure later, what we call the sea of electron model for metals. If you imagine iron or copper, they have a lot of valence electrons. So if you imagine this, say, being copper, copper has, if we're thinking of counting the 10d electrons, which you normally don't count, plus the 4s. So if you remember, copper is a 4s1, 3d10 configuration. It's one of those weird anomalies. It also forms a copper 2+ ion. So I'm thinking for copper that we have probably a lot of valence electrons, especially since I know it's going to a copper 2+ in some sense. I'm thinking this might be a weird case where some of these electrons are acting as electrons that are part of the valence shell of copper, that I might have up to 11 valence electrons for one copper atom. Now, one of these coppers doesn't have necessarily 11 electrons that it owns, if you will. What it has is all of the valence electrons for all the metals just surrounding the metal. There's a picture in a couple slides that'll show this. But if you imagine all those electrons being interdispersed, that we have almost like all those electrons surrounding the metal, if I can find a way to like pluck one of those electrons off, I remove an electron, I create a positive charge here, then all the other electrons flow towards that positive charge very quickly. And the same thing, if I put a negative charge, if I introduce a negative charge here, then all the electrons can just flow away from it very quickly. So that's the sort of idea of conductibility. A metal can conduct really well if it can sort of sense that charge and react to it and respond very easily and very quickly. And so metals do this well. They have effectively what we call no band gap, so no energy required to eject or exchange that electron to cause that conduction. We end up with high melting points and boiling points. If we look at a few examples, magnesium, 650 degrees C, silver, 962, titanium, 1668, tungsten all the way at 3400. Tungsten's used in light bulbs. You think of a tungsten filament, which are kind of on their way out of use in light bulbs. But tungsten filament light bulbs are the ones that get really hot. They get really hot in part due to just how much heat tungsten can absorb. And so really hot for a tungsten lamp being used. And so high melting points, high boiling points for our metals. Now, interestingly, like this probably isn't a property that'll come up anywhere, but if you look at, say, the alkali metals, it's actually cesium that's the lowest melting point. Metals are exchanging charge. Exchanging charge is easiest when you're smaller. And so it's going to be lithium that actually has the highest melting point. And that also helps us then maybe explain when we get over to mercury, why mercury being the biggest, usually we think biggest is going to have the strongest metallic bond. It actually has the weakest metallic bond such that it's a liquid at room temperature. And so cesium was actually very close. Cesium's melting point's like, I think, 28 or 29 degrees C. So if room temperature was 30 degrees C, cesium's a liquid at room temperature. So cesium was pretty close to being the third liquid element if surface temperature, at standard temperature was just a little bit hotter. And so then, so with size being bigger, metals are having to exchange charge, and that's a weaker charge that's being exchanged due to the increased size. And so this is just another example of when we're exchanging charge, we want things to be smaller. So smaller will have a stronger attractive force. Okay, so let's talk about a few other things with metals. This is that sea of electron model here I was referring to. So if you imagine having all these electrons around all the nuclei of the atoms, you can't really point to which of the electrons belong to which of the atoms. Now, this is usually something you can do with covalent bonds where you can say, okay, I have 2 electrons here, 2 electrons here, I have valence electrons on O, and you can sort of imagine that at any given moment, those electrons are kind of right where you think they are. Maybe not precisely where they are, but that there should be 2 electrons between the nuclei of H and O, 2 other electrons between the other H and O. And even in the case of an ionic solid, it's like you know that chlorine has picked up those extra electrons, and you know that they're kind of on that particular chlorine atom. Now, when you're looking at a given metal, these electrons here, they can be any of the metal's electrons. They're just kind of exchanging their electrons. The electrons are almost flowing through the structure. So if you imagine metallic bonding in this way, it's almost kind of like a third type of bonding. It's like we have covalent bonds, 2 electrons here. We have the sharing of bonds. We have the donation of bonds, and then here is just like the complete unownership of electrons. It's the complete sharing of electrons. And so like discrete sharing, and then like complete sharing with the sea of electron model. And so then this here is where if you can pluck this electron away here, you create a positive charge that the other electrons can respond by flowing towards. And so this hopefully helps show that conductive property of our metals. And then also, if you think of the malleability and ductile problem, if you start moving the nuclei, the electrons just flow with it. So the electrons just kind of go with the nuclei. So that's why you can pound metals into sheets, stretch them into wires relatively easily. It's just as you start moving the metal atoms, the electrons just flow and stay with the metals and rearrange themselves accordingly. This slide here, I just wanted to show this because I think it's kind of interesting, especially since we mentioned tungsten having such a high melting point, that some of the metals do start to take on more of a molecular type behavior, in particular in the middle of our transition metal row. And so this would be the first 2 elements in a group, like potassium, calcium, for example. And then the 3 through the 1b, these are the next 10 elements. So these would be the transition metals. And so our transition metals will increase until the middle of the group. And then it's the middle of the group of the transition metals. So it's like the manganese iron kind of group of elements, chromium, manganese, iron that have the highest melting points. And if you go the next row down, they're actually higher. So you can imagine that if we're now becoming larger in size and melting points going up, then these metals are behaving almost more like nonmetals. So you almost get more of a non-metallic behavior, where being bigger is now better. And so tungsten here was one of the elements with, that's actually not tungsten, tungsten's right here, but tungsten and then rhenium and osmium, those are the elements that have some of the highest melting points for metals. Not something I expect that you memorize or anything that I expect that you take away, other than that there's like an increase towards the middle of the D block, and then there's a decrease in melting point as we move away from the middle of the D block. And then we're going really low in the case of mercury. So kind of interesting behavior for metals. And so I just wanted to show metals have a wide range of melting points too. So we're seeing some metals, relatively low metals. On the case of the mercury, cadmium, zinc, relatively low melting points, also relatively low in the case of the alkali metals, and then a lot higher in the middle. So just kind of thought I would show the wide range of melting points of some different types of metals. So non-metallic behavior is what that's supposed to say. Okay, so the idea of nonmetals is when nonmetals are bigger, they have higher melting points and boiling points. Like F2, Cl2, Br2, I2, we're increasing in boiling point and melting point as we go bigger because those nonmetals, as they're bigger, can exchange charge better. We're seeing the same behavior with some metals in the middle of our transition metal row. Okay, now on the topic of crystalline versus amorphous solids, now what does this mean? So a crystalline solid, the atoms will adopt an ordered repeating pattern. We'll see a couple examples of this, but not in such a way that you have to expect or understand how to predict what the repeating pattern is. But a crystalline solid, the atoms in the solid adopt a very regular pattern. And so when a crystalline solid forms, it gives the substance a brighter appearance. It appears with more color usually. And it's because when light hits the metal, because the structure is the same at all points, light reflects off it very repeatably. And so we get like a nice smooth surface. You get pretty colors usually with crystals. When you have something amorphous, what an amorphous structure is, it's almost like we take all these atoms and we just randomly distribute those atoms through the structure. And so instead of having a regular pattern where there's some specific connection of like this atom to this atom to this atom, and that structure replicates in 3 dimensions, it's just like we took all those atoms, melted them down, and just froze them whatever orientation they happen to be in. And so then for an amorphous structure, you don't have an order like the crystalline solid does, so you end up having a more random structure. And so when light hits it, it might bounce off in different ways. And so the structure here doesn't appear to be as brilliant, not as bright, appears more dull. So you get a more dull appearance here. You get a more brilliant or bright appearance here for the crystalline solid. So crystals appear brighter, more colorful. The amorphous solids, not as interesting in that regard. And there's a few examples of this to show. One of them is this. This is like, I don't think I even needed to show this semester, but I just really like this series of slides. I made this a long time ago. Like quartz is a crystal that you can mine. And the crystal, it's not like a perfect crystal, so it's not like one color, it's not super bright, but it has a much more brilliant appearance than, say, glass does. So what quartz is, it's SiO2 with a more ordered pattern. Not a perfect ordered pattern. It's kind of like, anybody in the room engaged already? Anybody get an engagement ring yet? Okay, everyone's young, that's good. Has anybody ever seen the grading scale of diamonds? Has anybody ever seen this before? Okay, when you go to get married and you go to buy an engagement ring, or you start to want to get an engagement ring, you'll start to learn that diamonds have like a grade. And as you get a better diamond, it costs a lot more money. And what that really means is if you look at the structure of a diamond where we say it's a perfect tetrahedral structure of all the carbon atoms, well, if you replace one of those carbons with a sulfur, then you get if you replace a lot of the carbons with sulfur, you get a more yellowish diamond. If you replace a couple, you get a less yellow diamond. So you'll see one of the grading scales for a diamond is its color. And so the more perfect the color, the more like ordered those atoms are all carbon. So every now and then you have a little kink in the structure where maybe one of the carbons is missing. And that gives it a little yet less brilliance, so it doesn't reflect light as well. And so that's another grading scale for a diamond. And so no crystal is perfect, or very few crystals are exactly 100% exactly as you expect. And so quartz is more ordered than, say, glass is, but it's not perfectly ordered because you can see it doesn't have a nice brilliant appearance where every part of the crystal looks the same. But you get a more regular pattern. If you notice, you're getting kind of like 6-membered rings of what looks like the silicon atom in the quartz structure. Now what glass does, how we make glass is we take quartz, melt it down, so we melt it to a really high temperature so it forms a liquid, and then we let it go flat and then you just freeze it. And what happens is the structure takes on all these different ring sizes. So you get all these different ordered patterns of the SiO2 group. They become more random in their structure instead of very specific in their structure, and then you lose that brilliance. And now it's interesting that glass ends up becoming perfectly clear. It makes it really useful for the way we use glass. But instead of the crystal having a nice crystal structure where it has a color, has a pattern, Glass has no pattern, so light can more easily just go straight through glass. So light is bouncing off of our quartz here, and it's just going straight through the glass. So kind of an interesting property for something like glass. So where glass is the amorphous structure, and then quartz, the way we mine it, is the crystalline structure. So we lose the crystal structure, we lose the brilliant appearance of quartz, but then we get a property that we use a lot in the case of glass. Now, interestingly, you can take quartz, melt it down, add boron to it, and you make what's called borosilicate glass. That's what's in Pyrex. So you can take quartz as you melt it down, put other things into it, get other structures. This is like where I was talking about. I didn't need to talk about this, but what if you do cobalt? Well, you get this thing, this is the joke I have, which is, oh, my kid tells me that's a vase. It's like, so that's cobalt glass. Yeah, cobalt, you get blue glass. And I'm like, I don't think that's a vase. So this is more cobalt glass. So, I don't know. I made this a long time ago. I was just wanted to show the slide. It's one of my favorite slides that I have that has almost no need to be shown. But cobalt, you can add different metals to the glass, and then the glass takes on the color of the metal. And so you can make things like cobalt glass. You can make red glass by adding metals that are red in color, etc., to make things like vases or whatever that other thing was. Okay, and so what about crystalline solids that are ions? So if we have ionic solid, NaCl forms a nice crystal. You can like make the crystal, you can like shave it down so it looks like an actual square shape. But the crystal here, we'd have alternating plus minuses. And again, this is going to reflect light in the same kind of regard. It's going to look more brilliant in appearance than, say, a frozen out molecular structure where you get atoms in just more of a random pattern. Now, the part where we don't really need to know too much is just how these metals or ions are connected. It turns out that NaCl is like end on end, meaning you go plus, minus, where all these spheres are just kind of connected in a nice row linearly in all three dimensions. So we just have an end on end connection of plus and minus ions for sodium chloride, and we're just getting the alternating plus minuses. Some classes we've broken down how you can look at a unit cell and break it apart into how many atoms it contains. Don't worry about doing that process today. Just see the idea here that ions tend to form a crystalline structure. So ionic solids tend to form a crystalline solid, and there's different types of crystal structures you get depending on the ionic solid. I don't want us to dwell too much on the different types of structures, but we get a few different types of crystal lattices for different types of ionic solids. And then we also get crystalline solids for the case of diamond and quartz, or diamond and graphite. Graphite is similar to diamond. It's the graphite's the more stable form of carbon, but graphite is two-dimensional sheets of carbon atoms, where diamond are three-dimensional arrays of carbon atoms. And so we've mentioned before that graphite sheets can be slid off of each other because they're only held together by that weaker intermolecular force. And so we can understand that one graphite sheet and another graphite sheet just held together by an ionic force, and they can be separated. That's how we're using graphite pencils when we use graphite pencils. And so then we get a crystal structure for things like our covalent network solids. We also get a crystal structure for metals. So metals tend to form a crystal structure too, and they're bonding. But we're not going to dwell on what that crystal structure is and working through any problems related to those crystal structures. Okay, so this point here, this is going to take us kind of through chapter 12. So the idea of chapter 12 will be if we show you a metal, it has metallic bonding. So like Fe solid, metallic bonding. Carbon diamond, covalent network bonding. If you have like lithium fluoride, ionic bonding. If you have something like F2, O2, if you have that as a solid, it's going to have the intermolecular forces of attraction holding that solid together. And so if I said, there's a few problems later, but in the review, we can start predicting melting point trends. Like if I said, what boils, this is actually a test question once, like what boils higher? Like which of those has the highest melting point? I can't tell you how many people said it was F2, just because F2 is biggest. It's not F2, it's lithium. And then after the test, students are like, how can it be lithium when it's the smallest? And I'm like, well, which one of them is a solid at room temperature? You know, like we know this is a gas. We know that's a noble gas. This is a gas. That's the metal. That's the solid. You know, so sometimes, you know, a given question is just using a little bit of common sense, but also just the idea that lithium has a different type of bonding. That's why it's a solid. Lithium is being linked together through metallic bonding, like the other metals are. And then our non-metallic elements are sharing electrons through covalent bonds, which are strong in nature, but then don't allow the atoms adjacent to each other to be linked together with the same type of bond. So weaker bonding between F2, neon, and O2, just that relatively weak dispersion force of attraction. Okay, so with that, let's talk a little bit about the final, and maybe today start to get into some review problems. So the final exam for our class is a week from Monday. It's in the morning. They haven't announced the room yet. It's usually here, but I'm not entirely sure it's going to be here. But it'll probably be in this room. But we'll let you know for sure by announcements on Carmen soon. I'll mention it in class if we know it by next Monday or Wednesday. The final is usually about 50 to 55 questions, but a little bit longer in length. So we get the full 2-hour period. It's about an hour and 40 minutes or so for the final. So that gives us more time than we had for the midterms. It's cumulative through chapters 1 through 12, and we're still skipping the same sections that we had skipped previously. So the sections we had skipped previously were, or some of the topics we skipped. We skipped the topic in chapter 3 on like CO2 and water working out a formula. I don't know if you guys, it's hard to say. Do you remember the problem we didn't teach you? But there's a problem in chapter 3 we didn't cover that we had noted in chapter 3. I think we covered all of chapter 4 except the very end section. There's a couple problems we weren't doing on the analysis, chemical analysis from chapter 4. Chapter 5, we weren't covering the last section on foods and fuels. I think we hit all of 6. 7, we only covered the first 4 sections. I think we got through all of 8. I think we got through all of 9, all of 10. We didn't cover the very last section of 11, and then, like we just said, just part of the first section of chapter of section 1 of chapter 12. And then some of those pictures towards the very end were just things that are interesting and not necessarily things you need to know. So the things to know out of chapter 12 are just the types of solids, some of their properties, and that's about it. I have some practice final packets posted on the daily quiz page. Like for the first 2, I note some questions that are from some topics that we didn't cover this semester. So just look at the little description that goes along with those practice finals in the daily quiz area. I think there's going to be just one Carmen practice final, and I think it is one of the PDFs, or it's based on one of the PDF files that's already posted. So you may end up taking already what is a Carmen quiz if you take one of the PDF exams, but maybe you can take it twice, I don't know. Now, I don't necessarily recommend jumping straight to practice finals. Like, do some review before you get into a practice final so that you can use the final to give yourself a chance to get some feedback on how the real exam might go. There's also things called these like chemistry Olympiad exams. Did anybody take an Olympiad exam ever? These are like competition style exams. These are for people like in an AP class who are like top of the class and might want to do like a competition against each other. But they give some good review problems because like a lot of the problems on those tests are very similar in nature to problems that we're covering. And I posted a few that I have marked up with some topics and questions that might be worth studying for our final. And then try to figure out what you need to study. Everybody might be weaker in a different topic or area than others, so try to identify what those areas are and spend most of your studying on those areas so you can build from your weaknesses and be as strong as you can going into the final. I have some extra office hours. So next week, I'll just run my office hours a little later, Monday and Wednesday than usual. Thursday, 10 to 11:30 in the morning, and then Friday afternoon, 1:30 to 2:45. So stop by. These are 2047 McPherson. So just stop by. No appointment needed. Just stop by if you have questions. There's a review with Dr. Nguyen on Thursday next week, 1:30 to 3:30 here in this room. It's also, I sent the info out. I forgot to paste the actual info for logging in. I'll send another email with the instructions if you wanted to join the Zoom session, or if you want to like make sure to be able to access Dr. Nguyen's YouTube channel to look at the review session after the fact if you want to use that to help you prepare for the final. Okay, with that, let's just get into a few review problems. The way I thought of structuring the review was to kind of go back to chapter 11, review some chapter 11 topics, then we'll get a couple of chapter 12 problems after that, and then we'll circle back and review some of the chapter 1 through 9 concepts, or 1 through 10 concepts. Okay, so we have a phase diagram here. So this is out of chapter 11. And so the things we need to know is that this is a solid, this is the liquid, this is the gas area. If point D, if this is the critical point, then this would be our supercritical fluid. And so let's see what we're we're asked which of the statements is false. And so the solid has a higher density than the liquid. And so if I imagine taking the solid here, and if I add pressure, so if I add to the pressure, I'm increasing the density. So if I push a solid closer together, I'm increasing its density. And you notice that by increasing the density, the liquid, it forms the liquid state. So that means the liquid is greater than the density of the solid. So the liquid has the greater density here, not the solid. So the solid has a lower density than the liquid. So this statement here would appear to be false. Now let's go through the others and make sure that they're true. B says sublimation and deposition. So sublimation and deposition is solid to gas. So the solid to gas transition is the only phase change possible at temperatures and pressures below point B. So that's point B. Point B is the triple point. So below the triple point, or at the triple point, is the coexistence of the three phases. It's where all three phases are in equilibrium with each other. But if you go below this point, then the solid can only go directly to the gas, and the gas can only go directly back to the solid. So that statement would be true. That sublimation deposition is indeed the only phase change possible below the triple point. No phase change occurs when the liquid phase is compressed at constant temperature. So if I take any substance here that's liquid and I compress it, meaning add pressure, I add pressure to the liquid phase, I stay a liquid. Now, for most substances, this is pretty abnormal. Most liquids, if you pressurize a liquid, will eventually form the solid, because if you take a liquid, press it closer together, you're usually going to form the solid phase. And so this is kind of an abnormal phase diagram, but no phase change can indeed occur when we pressurize a liquid. So when heated at 1 atmosphere, we have 1 atmosphere shown here, the substance will first melt, then boil. Yep, so we go from solid to liquid to gas. And so that just means at standard atmospheric pressure, you undergo the normal process of melting and boiling. If you recall, for something like CO2, its triple point was like 6 atmospheres, and so below 6 atmospheres at 1 atm, CO2 can only go from solid CO2 to gaseous CO2. So we skip the liquid phase for substances that have a high triple point pressure. So we can indeed go through the normal melting and boiling processes at 1 atmosphere. And it's possible this is for water. This is actually probably water's phase diagram. So water has the property of having the solid with a lower density than the liquid, and then also undergoes like a normal melting and boiling process. So this could indeed be that of water. So the only statement here that would appear to be false is the one that says the solid has a higher density than the liquid. Let's move on to this question here. So the vapor pressure of CH3F is 3.3 megapascals. Don't worry so much about the unit, but let's just compare to the magnitude of CH3Cl, which has a lower vapor pressure. And so what does it mean to have a lower vapor pressure? Does that mean that this compound here with a lower vapor pressure, does CH3Cl have a stronger intermolecular force than CH3F or a weaker intermolecular force? It has to have a stronger intermolecular force, because the stronger intermolecular force is what's not allowing its vapors to escape into the vapor phase. And so if a liquid has a stronger force, if it's going to hold on to its molecules more tightly, it's going to have a lower vapor pressure as a result, because it's harder for those molecules to escape into their gas phase. And so now, why might that be the case? So why might CH3Cl have a stronger force of attraction with itself than CH3F does? CH3F, we think fluoride's smaller, more polar, so we probably get a more polar bond for CH3F, but it's also smaller. And so where CH3Cl is probably benefiting is by having that stronger dispersion force by being bigger. And so likely here we have a stronger dispersion force, despite the fact that we might think that the dipole-dipole force would probably be higher and stronger for CH3F. And so what explains the difference here? So probably what explains the difference is the greater dispersion force in the methyl chloride. So we have a stronger dispersion force, which increases its intermolecular force of attraction compared to CH3F. Now let's go through why the other reasons wouldn't be correct. So the electronegativity of F versus Cl would point toward a stronger dipole-dipole force, which would point towards CH3F having the stronger intermolecular force. So the reason why this is wrong is if that were the explanation, it would have made CH3F have the lower vapor pressure, but it has the higher vapor pressure. If we had a stronger dipole-dipole force in CH3F, again, this would be the explanation if the trend were the opposite. The strength of the covalent bonds. See, covalent bonds are not being broken here, so the strength of covalent bonds is completely irrelevant. So this is completely irrelevant here on how strong the actual covalent bonds are within the molecule. It's all about the two molecules side by side, what's their intermolecular force of attraction. The strength of the covalent bonds within the structure doesn't matter. So when you look at water bonded, or right next to a water molecule, we're not changing or breaking or doing anything to the covalent bonds. It's all about what's the nature of the negative charge that O ends up with that can interact with the charge that the H's end up with. So it's all about the electrostatic forces of attraction, the H bonding forces for water, and the case here are higher dispersion force for CH3Cl. Hydrogen bonding does not form. Like there is no hydrogen bond in CH3F. So if I look at CH3F, my structure looks like this. I need F directly attached to NO or F. It's directly attached to a carbon. So there's no hydrogen bond. I just want to make sure that we see this, that we have no hydrogen bonding intermolecular force in CH3F. So sometimes we see F, we think, oh, it has hydrogen bonding force of attraction because of fluorine. We need F to be directly attached to NO or F. The only case with fluorine would be HF. That's the only molecule that forms hydrogen bonds with fluorine. That's because fluorine only forms one bond. It's either directly bonded to H, therefore an HF, or it doesn't form hydrogen bonds. Okay, so let's move on from here. Look at maybe another question or two. Let me skip this one for later because it doesn't have anything to do. It's from an earlier chapter. But let's look at what occurs when liquid CH2F2 evaporates. So CH2F2, if I'm sketching a Lewis structure, I might sketch this one here. Just making sure to understand how to get to the Lewis structure, where I have 4 for carbon, 2 for the hydrogens, plus 2 times 7 for the fluorines. I have a total of 20 electrons, so I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons distributed. Just making sure I can get to the right Lewis structure, but then I have to be able to realize that the real structure is tetrahedral, not 90-degree bond angles, but 109-degree bond angles. And so this molecule here is definitely going to be polar. We're definitely going to get that dipole-dipole force of attraction. Definitely going to have dispersion forces. But again, no hydrogen bonding forces. And so when the liquid evaporates, so if we have liquid CH2F2, it's going to evaporate into the gas phase. What has to be overcome are dispersion forces. I have to overcome dipole-dipole forces. There's no H bonding forces, not part of the question, but no hydrogen bonding forces need to be broken between molecules because there is no H bonding force. And then none of the covalent bonds are broken. So we're not breaking the bonds here. We're not breaking any of these bonds when we go into the liquid. We're just breaking the bonds that hold adjacent molecules together. So only 1 and 2. And then also, again, no H bonds. No hydrogen bonding forces. All right, fast, sorry. Okay, so sometimes we see F, we think hydrogen bonding forces. Again, you need F directly bonded to H. Let's look at the second question here. It's pretty quick, and we'll end on this one. Which of the following properties generally decreases as strength of intermolecular forces increase? Most properties increase with increasing intermolecular forces. Enthalpy of vaporization, stronger intermolecular forces, this becomes higher. The normal boiling point, stronger forces, harder to boil. higher boiling point. The extended deviations from an ideal gas law, as we have stronger intermolecular forces, we're going to get a greater deviation, right? The B factor is directly proportional to intermolecular forces. So higher intermolecular forces, higher B, greater deviations with the ideal gas law. Tricky question, but that's going to deviate there. The sublimation of a solid, that phase change directly proportional to the strengths of intermolecular forces because the phase change of fusion is, the phase change of vaporization is, sublimation is just the sum of the two. But then the vapor pressure. I mean, I think if you looked at this question, the answer had to be vapor pressure because that's the only property that goes inverse. That's the one where harder for the molecules to escape into the gas phase with stronger intermolecular forces. So that's the one that becomes lower. Lower vapor pressure with stronger intermolecular forces. We'll revisit question 1. We'll eventually revisit the part B of question from the last page and then the other questions in this packet next week. All right, guys, thanks for the attention today and have a great weekend. And go Louisville, go whoever Texas is playing. Get us into the playoff, guys. Let's go.